introduce Gary. I've known Gary for years now, and I've always noticed that he's equally adept talking about technical issues and about business issues. And then when I saw his bio for this webinar, I realized why, because he's got a couple of power engineering degrees and an MBA, so he's not just faking it. He actually knows what he's talking about. Gary is one of the thought leaders of our industry, and we're real happy to have him here. And Gary, I'll ask you to take it away and continue. Thanks.
Thanks, Jesse. This slide is just looking at some of the different types of sensors for power transformers. So if you recall that process slide that I showed previously, going from the asset all the way to work in asset management and how you can manage the process with this approach, I just wanted to touch on the sensors. And when our algorithms are built around being able to take in nearly 70 different types of inputs, and these are just some examples. If you look at the middle two, the acoustic emission and also the load tap changer, gas and oil, and contact wear, that is focused on LTCs, the load tap changers, and we're doing actually some development work with a utility in Canada around the acoustic signatures associated with the operation of load tap changers and how we can benchmark that and then track if there's any variation. But looking at the standard oil test, looking at dissolved gases in the oil, also utilizing partial discharge to detect any breakdowns of insulation. Also, we can look at bushings in terms of partial discharge. Frequency response analysis, looking at the inductance and capacitance of the windings to make sure there isn't any damage or if they have moved either because of a through fault or possibly from transportation. So we can integrate all of those different sensors and capabilities into the process. So what I just discussed with the sensors is what's shown at the top of this particular slide, the online sensor data. But we also take in the SCADA data, which is shown on the left, and this would come from the historian. So there's a baseline or in terms of a transformer fingerprint, but also events, alarms, load on the unit, oil temperature, ambient temperature, tap position, etc. And then at the bottom is the offline database information that can be incorporated, which is the maintenance reports, inspection reports, routine tests, standard oil tests, Furans analysis, which gives you an indication of if there's any insulation breakdown, offline dissolved gas analysis. And we integrate all of that into the performance models to determine what is the health of the asset. MTMP, shown in the middle, is basically that process which is more based on static information. But what we have done with the business intelligence platform and the automation of the data collection is move to a dynamic transformer management program. So this slide shows what you can do when you do this dynamically, which is you can have a continuous process, which is capturing the information from these three different types of sources, continuously processing it, and then visually displaying the status and condition of those assets on a continuous or ongoing basis. So there is no stranded information, no information is lost, or heaven forbid somebody look at the data after the fact when a failure occurs and realize they might have been able to prevent it if they'd been more diligent in looking at the information that they had available. This process captures that and makes it available to the enterprise. Some of the screens that are available, I have some sample screens in here. What this is showing in the upper left-hand corner is basically a summary slide that gives asset details. This is actually showing transformers, showing different classes of transformers, sub-transmission, 230 and 345 kV units, and then 500 and 765 kV units. On the middle right is a total risk of failure, and I'm going to come back to that visual because that's an important attribute of what the Asset Health Center can offer. But again, this is just a high-level overview slide. But we can look at individual assets, which are shown in the drill down in terms of the summary, the trending, the messages and notification. From gas analysis, we can look at Duval triangle analysis to determine what's the likely cause or source of the gas and how the transformer is performing and if there's damage and to what extent. What's also interesting is we can track that over time. People talk about cookie crumbs. You can basically track the analysis over time to see how the transformer is changing. You can see if there's a change in its performance or its rating when you process the oil, And so we can track all of that over time. And then the last slide, the health index. This is taking those 68 or as much information as you have available, different parameters, and then calculating what the health and condition of the asset is. This is all user configurable. We can take the information you have. You don't need all 68 different parameters that we can look at. We can run with what's currently available and leverage that information. And then through the ongoing process, identify maybe you should add different sensor technologies to address certain problems that you may have on some of the units, and you can really fine-tune that process based on available information. I just wanted to talk briefly on breakers. This just shows some example of the sensors that are available. Looking at SF6 gas and being able to tightly monitor that because it is a greenhouse gas is important to utilities and also for compliance issues. But in breakers, we're looking at 4 main subsystems. The SF6 gas system, the interrupter, the mechanical system, and then the electrical controls and auxiliary. And the benefits are the same. It's an automatic processing of data and capturing of data, and we're really driving increasing reliability and identifying potential problems early. And again, we're pushing the condition-based maintenance because you maintain what's needed, when it's needed, and you can be more efficient with your O&M budget. This slide provides a little bit more visualization into the different categories and what type of parameters are captured by the sensors that I just showed. So in the upper left, the SF6 gas, again, we're looking at temperature, pressure, trying to make sure that we don't detect any leaks. We can also check on possibility of any contaminants in the gas as well. The lower left is the interrupter wear. This is largely based on looking at the I²T in terms of the amount of energy that's interrupted whenever the breaker does open, and then tracking that. The mechanical system is looking at both reaction time as well as travel time to make sure that there's not a change in the contact velocity of the interrupters. And then the auxiliaries are shown in the upper right-hand corner in terms of monitoring the cabinet and all of the auxiliaries associated with the breaker. This is just showing, depending upon the type of sensors that you have available on the breaker, you can actually directly monitor the contact velocity. With a relay, you can capture the total reaction time to breaker opening time. It gives you an indication of the health of the mechanism, but doesn't give you the same level of information in terms of the contact velocity, which is actually important to know in terms of the interrupter wear. But this is the type of data that we're looking at and processing as a result of the monitoring and the sensor technology that's currently available. So I mentioned that total risk of failure chart, and this really shows what we're driving towards in terms of asset health, because we look at the risk of failure, which is a function of the health of the asset, which is based on all the different parameters that are being monitored. We do apply some weighting factors, and we come up with what we think is the condition or health of the asset. But the other parameter is how important is the asset? A cornfield distribution substation transformer is not nearly as important as a generation step-up unit, that's basically handling the output of a nuclear power plant. So that criticality and that unit importance is what we think is a very important dimension. So we look at both factors when looking at total risk of failure and in how O&M money should be directed towards making sure that as many of the units are in the green as possible, and then making investment decisions and life cycle management decisions on the units that persist in the red. So this is an important diagram in terms of summarizing health of the fleet and then also driving specific actions on each of the individual assets. And an asset can be tracked in terms of where it is on importance. If it moves from a spare to in service, that's going to change its importance, and we can track all of that in this type of display. So what we're doing is we're using analytics to move from trending and just basic alarming to being able to predict and forecast performance of assets. That's what that total risk of failure is based on the asset health and condition of the assets. The other thing that we're able to do with the analytics is we're able to optimize. We're able to direct O&M expense based on condition of assets, which means the items that need to be maintained are being maintained when it's optimal to do so. And this really captures the migration of the industry and what utility analytics is really enabling as it applies to asset health. Just as Jesse mentioned in his opening comments, it's much more efficient if you can address a problem prior to a failure, particularly a catastrophic failure. And this is some research that ARC did that we just provide, which reinforces routine maintenance on an as-needed basis is far more effective than reactive repairs or maintenance whenever a problem occurs in the field. I think this is turning it over to you, Jesse.
Yes, thank you. And we just heard from Gary Ratcliffe of ABB as he explained this end-to-end asset health idea. And right before that, we heard briefly from Chris LeMay of Ventyx as he laid out the challenges and opportunities. Now we're going to pause for a few questions. I've got a question from Marc-Andre, and he wants to know how asset health might help Gary in asset investment planning and in making the rate case. I might just expand that to say that in Europe and Canada, especially in Europe, I know the trend is for regulators to ask for this, quote-unquote scientific assessment when deciding which assets to upgrade or replace. And I'm wondering if you're seeing any of that trend in the U.S.
The answer is yes. I think it's a major challenge that utilities have, which is engineers translating what they view as the scientific or engineering reasoning behind making a recommendation for an asset replacement versus how that gets translated into financial need, financial priority, and actually getting the capital to make that investment. Having a snapshot is great, but having a history of performance of the asset and its condition and how that is changing over time, as well as knowing the design and the history of that particular asset's design and what its performance has been in the field, gives far more consistency, repeatability, and transparency to the decision process for making asset investments. And we view having that data available on an individual asset basis as well as a family of assets or an asset class against which the asset can be benchmarked enables better decision processes regarding asset investment. And it's transparent, it's repeatable, you get the same answer if you do the assessment twice, and I think that facilitates investment processes.
So a follow-on question to that is, does the formula include impact on SAIDI?
We can, although we haven't done much work. SAIDI is more driven by the distribution system, and we've been more focused on transmission assets, although I do recognize there are transmission outages which do affect end-use customers, but they tend to be limited in occurrence. At the distribution level, we have done work around asset performance and its impact on reliability, of which SAIDI is a metric in terms of, SAIDI would be system duration. So that type of analysis can be done. We haven't done as much work because our initial focus has been more on the transmission assets.
Well, and that brings up Christopher's question, because he wants to know if you see asset management trickling down to distribution assets, especially since more and more of the equipment is shipping with sensors.
Absolutely. As there are more and more sensors and there are more distribution assets in terms of total number of assets than we see at the transmission level, there's a need to be able to manage and process that information. So absolutely. But if you factor in that criticality piece, the distribution assets, even though they need to be maintained, inspected, and they do, if a failure can cause a customer interruption, the number of customers that tend to get impacted are far less. And so I think there needs to be a balance between how critical the asset is, as well as making sure that you capture what its health is and you process the available data. So again, we see more utilities focusing on transmission assets first and then moving down to the various voltage classes, starting to focus on the distribution assets. If you look at a distribution transformer at the other end of the spectrum, people may put sensors and monitors on that, but you have to factor the cost of going out and replacing that transformer versus if it fails, what's the cost of failure going to be.